In the first part, I mentioned the importance of cab safety and the design of a rollover protective structure and the falling object protective structure, or short ROPS and FOPS. For our concept, we wanted to prove that a fully bonded cab structure can withstand the loads that are necessary to protect the operator. We conceptualized an off-highway vehicle with a mass of 8.5 tons or around 18,700 pounds. From this, we derived the ROPS and FOPS requirements given by the standards. An initial calculation showed that the FOPS test was more critical for our conceptualized vehicle. Therefore, we set out to first test the FOPS requirements in an experiment and compare that with a finite element model that we set up. The validated finite element model was then used to also prove the ROPS capabilities. Let's first have a look at the setup for the FOPS test. For the FOPS test, we assumed a worst case for the node connection where an object is falling directly onto the hollow structure. The impactor mass of 250 kilograms is then dropped from 2.9 meters, reaching a velocity of around 25 kilometers per hour. So you can see there is some substantial load on the connection. How does the connection hold up to such loads? A speckle pattern is applied to monitor the displacements. The impactor hits the hollow structure and deforms it, but overall the connection at the nose stays intact. Because the impact of the mass can be stopped and the displacement is limited, the safety of the operator is ensured. Since the impact happens quite fast, let's have a look in slow motion. Though some movement at the connection is visible, the slide down of the hollow section is prevented by the adhesive bond. You can see that a lot of things are happening during the impact. We wanted to see if we can replicate this behavior in a model and use this model to validate our ROPS requirements. We set up a dynamic finite element model in radius reflecting the real impact test. For the node and the square hollow section, we chose an elastoplastic material model. S355 steel properties are assigned to both parts. The adhesive is modeled by a so-called connection material, which is similar to cohesive zone materials. This is an effective way to model adhesives in dynamic simulations. SikaPower 1277 properties are assigned to the adhesive, the same adhesive that was used in the experiment. Looking at the simulation, the behavior is very similar to the experiment. The impactor deforms the hollow structure significantly, but overall the connection at this node stays intact. Looking at the experiment and simulation side by side, it is obvious that both show very similar characteristics. The deformation of the hollow section as well as the restricted movement of the hollow section at the nodes is clear. Finally, the overall deformation, a key characteristic to protect the operator, is quite well met. This shows very well that even complex events like the impact can be modeled with good precision, even when adhesives are involved. With the confidence in our model, we set out to evaluate the ROPS load case. For the ROPS test, 3 different load directions are relevant: vertical, lateral and longitudinal. On this slide you can see the deformations as a result of these 3 different load directions. You can see that the maximum displacement is coming from the vertical load. The deformation is significantly less than the one from the FOPS test. Finally, the structure is able to withstand the loads needed to protect the operator. Since we didn't see a complete failure of the adhesive bond in the test, we were curious how much load it would take to destroy the connection. Therefore, we set up a tensile test with a node clamped on one side and the hollow structure at the other side. In the test, we pulled up to 100 kN, which was the limit of the test equipment. This is the equivalent of around 10 tons or 22,500 pounds, and we could not destroy the connection. For our design, we aim to reach the yielding of the hollow structure. As previously mentioned, this can be achieved by adapting the bonding area to the dimensions and properties of the hollow structure. This experimental and simulation result demonstrate the exceptional strength and durability of the adhesively bonded connection, further validating the potential of this innovative solution for improving safety and efficiency in off-highway vehicles and other industries.